The generator in this problem consists of a magnetic field and a rotating armature. I'll draw the magnetic field here in green, directed out of the screen towards us. The armature is in the shape of a square and it has 120 turns. Its area is a vector that is perpendicular to the plane that could be either into or out of the screen in the orientation I've shown here. I'll draw it out of the screen, parallel to the magnetic field. It rotates around an axis at an angular speed omega that we're asked to calculate. First, let's find the magnetic flux through one turn of this armature. That's the integral of the magnetic field over the loop's area. Because the magnetic field is constant over the loop, this is just the dot product of the magnetic field vector and the area vector, where theta is the angle between those two vectors. We know from Faraday's law that the EMF induced around the armature is minus the time derivative of the magnetic flux through one turn multiplied by the number of turns, capital N. In our expression for flux above, the only variable that changes with time is the angle theta. As the armature rotates, the angle between A and B changes with time. So we can calculate the time derivative of the flux using the chain rule. It equals minus NBA sine of theta times d theta dt, which is the angular speed omega we're asked to calculate. The maximum value of this EMF occurs when sine of theta equals -1, canceling the negative sign and maximizing the function. So the maximum EMF is NBA omega. We can solve this for the angular speed omega. It equals the maximum EMF divided by the number of turns times the magnetic field magnitude times the loop area A. When you substitute values and calculate, you find that it equals 10.4 radians per second.